When you read Chapter 2, you read a little bit about the older models of the atom, from Dalton's original billiard ball model to Thomson's plum pudding model after he discovered the electron through the cathode ray experiment, and then into Rutherford's nuclear model after he discovered the nucleus using his gold foil experiment. In this chapter, we're going to pick up from there, go into some more modern models of the atom, and then we'll talk about electron position, electron location, the different orbitals that they'll be in, and all of their properties. And then in the next chapter, we're going to be discussing the trends that you can determine based on an element's position in the periodic table. This particular video, what we're going to be doing is we're going to be doing a little bit of review on electromagnetic radiation. You may have seen this a little bit before in 10th grade or in physics last year. You are going to need something to write with. You're going to need something to write on. You don't need a calculator for today because we're going to do the math in class, but once you have those things ready, let's go. Okay, so what we should do is we're going to start off talking about waves and then light a little bit. Right, so just a brief definition, a wave is a disturbance that travels through some medium. Right, so a sound wave is a regular disturbance that travels through air. Waves in the ocean, disturbance that travels through water. Now, what we care about for our purposes in a wave is we care about three different variables. We care about wavelength, which is the distance between two consecutive peaks of a wave. Frequency, which is how many waves travel through a given point every second. And the speed of a wave, which is how fast it's traveling through its medium. Now, if you look at the unit for frequency, frequency is measured in hertz, which means cycles per second, or you'll also see it referred to by the unit of reciprocal second. Okay, and the Greek letters there, if you want to use F for frequency, because I know some of you did that earlier, that's perfectly fine. It's just that you'll see it in traditional equations as lambda for wavelength, nu for frequency, and speed is going to be c. And the speed of a wave is the frequency times the wavelength for any given wave that you can work with in this case. Now, while ocean waves and sound waves are nice, what we care about is we care about electromagnetic waves. Electromagnetic waves are also called electromagnetic radiation. The key distinguishing feature of this is that the speed that it travels at is the speed of light. So any wave which travels at the speed of light in a vacuum is an electromagnetic wave. And as you can see in the diagram, the electromagnetic spectrum has a lot of different proportions or parts to it. Right? We have our very low energy, long wavelength radio waves. So your AM radio waves, for example, have wavelengths that are measured in the order of miles. Right, then we move up, we get microwaves, so what they use to heat up a microwave oven, infrared, visible light, ultraviolet, X-rays, and then finally the highest energy, the highest frequency, the shortest wavelength rays are the gamma radiation. Right, notice how the visible light, the visible spectrum, is just a very, very small band in that electromagnetic spectrum. It only covers between 400 and 750 nanometers. Everything that we can see is in that small range. Alright, so electromagnetic radiation travels at the speed of light. That's this key distinguishing feature. Now, we can move on a little bit from that, and we can also talk about the energy of light. The energy of light, a lot of work for this was done by Max Planck and Albert Einstein. Right, Planck, through his black body experiment, for those of you who are unfamiliar with the experiment, is basically the idea that when you heat a solid, that solid will sometimes glow. Right, and the color that it glows is dependent on the temperature which you heat it to. So, for example, if it glows reddish orange, that's a very low temperature. But if it glows like a very bright bluish white, that indicates a very high temperature. So what Planck hypothesized is that energy has to only exist in very small specific values called quanta, or the fact that energy is quantized. Right, so the way to think about energy is that energy is not like a ramp that you walk up. It's more like walking up the stairs. So you have a stair with a specific amount of energy, then you add a quanta and you get the next stair, you add a quanta and you get the stair after that. Einstein took this and ran with it. So in his work on the photoelectric effect, which is actually what he won his first Nobel Prize for, the photoelectric effect is just the idea that if you shine light on a metal plate, you can actually occasionally eject electrons from the surface of that metal plate. And what he showed was that the light had to have a given minimum frequency in order to eject those electrons. Now, you can correlate frequency of a light wave to the energy of the light particles, called photons, that were there. So the energy of a photon is h, which is Planck's constant, times the frequency. Okay, so if your photon has that minimum energy required to unbind the electron from the atom, it can be lost. That's the photoelectric effect. Okay, so that was just a brief review of light. Like I said, we'll save the equations for light until we get into class. But in our next video, what we'll do is we'll move forward and talk about how this idea of quantization of energy and light was used by Niels Bohr to create his Bohr model of the atom.